Alright, in this video we're going to be looking at the very basics of probability. Not too much at the beginning, just to give you a feel for it. So we'll start with flipping a single coin. There's a couple of things I want you to know about it, at least the way we're going to deal with it in this class. Heads or tails is equally likely. We're not going to get into game playing that one has a small percentage more than the other one. We're just going to assume that each side is likely, equally as likely. Number two, the coin never lands on an edge. So we'll call this honest probability if you want. The chances of getting a heads or a tails is equally likely. So we know that if you flip a coin once, you will get either heads or tails, and that's it. In fact, if we wanted to, the chances of getting either heads or tails, so I'm using the phrase or, is 100%. When you flip a coin, you are going to get heads or tails, and so there's no question that the total of all those possible outcomes is all the possible outcomes. So when I look at it, I can write something like this: P, meaning probability, and then I can put inside of the parentheses P, H, or T. That means what's the probability of heads or tails occurring, and that's 100%. But now on the other hand, we know that the two of them have the same probability of occurring. So the probability of heads is the same as the probability of tails. Now let me write something here. S will consist, it's a set consisting of two items, H and T. This S that I wrote is called the sample space. And it shows all of the possible outcomes. Let me underline that word, the word sample space. And then let me draw this n parenthesis s, that equals 2. This is the number of items in set S. So whenever I put an n in front of something, I'm talking about the number of items. Now, what is the probability of heads? Well, what we do is we set up something called an event. E equals the set H. This will be called the event of getting a heads. And then the way we define a probability, if I want the probability of heads, what I do is I take the number of items in the event and divided by the number of items in the sample space. This is only true when the total number of items in the sample space is finite, which is the case here. We only have 2 items there. The size of our event, there was only 1 item in the event and there was 2 items in the sample space. So the probability of getting heads is 1/2. Or if you want, you could write it as 0.5, or if you want, you could write it as 50%. Although 1/2 will probably end up being the most useful. So then, because I know the probability of heads is the same as probability of tails, I also know that the probability of tails is equal to 1/2. And of course, if I take the two of them and add them together, I get 1. So as long as we're doing these, we want to keep the examples simple. So with that in mind, let's do an example rolling a single die. So roll a single 6-sided die once. What is the probability of getting a 3? So we're going to do the same thing. Now, the formulas that I'm writing down are useful only for when each of the outcomes is equally likely. So when we roll a die, a lot of times you'll see authors put this in here. That indicates that each of the 6 possibilities is equally likely to occur. And of course, we want that in here. So to get this then, let's take a look at our event. The event is just the number 3, and the sample space has all the whole numbers up till 6. So if I want the probability of a 3, that's the size of the sample space, and I just said it backwards, that's the size of the event divided by the size of the sample space, and so you get 1 out of 6. Now here, it would destroy the understanding of that fraction if you were to go and do something like this and get the decimal like that. Looking at 0.16 with a bar over it does not show me that we're talking about 1 out of 6, which the 1 divided by 6 does. So I think many times the fraction will actually tell us more information than just putting it as a decimal. Well, let's continue here. What is the probability of getting an even number? So let me separate that from the previous one. Actually, you know what? Let me keep that in there because I do want it to be part of the same example. So to get the probability of an even number, let's take a look at our new event. The event this time will be 2, 4, and 6. But the S will be the same as it was before. And so if I want the probability of an even number, that's going to be the size of event E divided by the size of the sample space. E is equal to 3 and the sample space is 6, and you could do it in 1/2. To me, 3 out of 6 tells a little more information than 1 out of 2. So I wouldn't always recommend simplifying, especially if it means understanding where the numbers come from. Well, let's continue with the die. Maybe I should put little stars here to indicate when I'm asking questions about it. So we'll do that again. What is the probability of getting a number that is both even and odd? Here, if I look at the event, there's no items in there. It's an empty event. Many times they'll put this, a 0 with a slice through it to indicate something called the null set. Either way, that was the event E. Either way, the size of E equals 0. So then when I look at the probability of, I think I'll just put E this time, that will equal n of E divided by n of S. That's 0 over 6, which is 0. So it can't happen, basically. Whenever a probability is 0, that means that whatever the event was cannot possibly happen. And we know that when you roll a die, you cannot get a number that is both even and odd. What is the probability of getting a number no more than 2? So for this one, my event E, I want to include all the numbers that are no more than 2, so that's less than or equal to 2. So in this case, my E is only consisting of 2 items, so then the probability of E, that'll be n of E divided by n of S. The size of E is 2, and S, of course, is 6. So you can leave it as 2/6 or 1/3 if you please. What is the probability of getting a number less than 3 or greater than 4? So once again, let's take a look at our E. The numbers that are less than 3, that's going to be 1 and 2, and the numbers that are greater than 4 is 5 and 6. So the probability of E equals n of E divided by n of S. That is 4 out of 6, or if you like, 2/3. Two future parents want to have 2 children. What is the probability that A, neither child is female, B, they have exactly 1 female? So first, let's take a look at what are all the possible outcomes that they can have here. So if I look at the sample space, what all can they have? They could have a male and then followed by another male. Or they could have a male first followed by a female. They could have a female first followed by a male. Or finally, they could have 2 females. So we see the size of this set is equal to 4. I've got 4 individual items in there, even though each of these is a compound item. Now for part A, let's start that. Neither child is female. So look at all the outcomes and tell me the ones that have no females in them. And the only one you'll see is the MM. And so the size of E equals 1. So the probability of no females is the size of the event divided by the size of the sample space. The size of the event is 1. The size of the sample space is 4. So the probability is 1/4. For part B, here the event is a little bit different. Now we want exactly one female. So look across all the possible outcomes and see which one of these have exactly one female. There's two females. There's no females. So these two in between are the only ones that involve exactly one female. So we have MF or FM. And so the size of the event is only 2. And so the probability of one female equals the size of the sample, or size of the event divided by the size of the sample space. So we get 2 out of 4, or 1/2. That makes sense, though. It should really make sense to you that the probability of having exactly one female would be 1/2, and the probability of having exactly one male is also 1/2. Suppose you take a 3-question true or false quiz and guess at every answer. What is the probability of getting one correct, 3 correct, 4 or more correct? Since you're guessing at every possible answer, each of these outcomes is equally likely. So let's go ahead and take a look at what the sample space could be. So let's take a look at some of the things you can possibly do on this exam. You can get none of them right. You can get 1, 2, or 3 of them right. So if we start getting none of them right, means that every single answer you answered was wrong. So we get wrong, wrong, wrong on all 3 of the questions. Next, we could be only wrong, we could be right in one of the questions. So I could have a wrong, wrong, correct, or I have a wrong, correct, wrong, or I have a correct, wrong, wrong. So those are the 3 possibilities with exactly one correct answer. Now, what about 2 correct answers? Here we could have something like CCW, CWC, or WCC. So all of those are all the ones where you have exactly 2 correct answers. And then finally, you have CCC, which is all 3 of them. So then the size of this sample space is, each of these blocks is just 1. So we've got 1, 2, 3, 4, 5, 6, 7, 8. And now let's go ahead and get our events in. For part 1, to get 1 correct, our event has to look like the places where you have just 1 C. So it's these 3 right in here. So we have WWC, WCW, or CWW. And then the size of E equals 3, so that the probability of this E occurring is N of E over N of S. And so that's 3 out of 8. For part B, to get 3 correct, here our event is only going to be the single solitary item, 3 C's. So N of that is equal to 1, and the probability of that equals 1/8. And then finally, 4 or more, well, if you take a look at this, there are no items in the sample space that have 4 C's or more. So E is called the empty set. The size of E equals 0, and the probability of E is 0 out of 8, which is just 0. Now, let me elucidate what we did a little bit better. And some of the things that we're using in here uses properties of counting. This sounds like an easy term, but it's not always as easy as you think. So let's take a look at our quiz that we were doing. Here, let's say, here's our starting point. Now, question 1, let's say here we have question 1. I'm going to put dots here. I'm going to make what's like a tree chart or a factor tree. It's going to look like a factor tree when I'm done. But let's say that this was question 1. Question 1, you either got correct or you got it wrong. Now, after question 1, after you got the first one correct, maybe you went on to the next one. And once again, your possibilities are that you get the next one correct or the next one wrong. Over here, if you got the first one wrong, we can continue and say, well, maybe you got the next one correct or you got the next one wrong. So basically, what I've uncovered here is 4 different outcomes. I've got a C so far for the first 2 questions, or I have a CW. Or I have a WC and a WW. So I have 4 possible outcomes just yet. That's only after 2 questions. For the third question, though, we can continue. I could get correct or wrong here. Correct or wrong. And finally, see if I can sneeze in. Correct or wrong, correct or wrong. Now follow each of these branches to get to what the event was. So starting along here, this is a CCC. Moving here, I get a CCW. Moving on here, get a CWC. Moving on, I get a CWW. Moving on, I get WCC. WCW. WWC. And then finally WWW. So you can see this here is the sample space. And you can see it consists of exactly 8 outcomes. For this last example, I've grabbed an example from the textbook, but I'm going to ask you different questions about it. So what we have here is a marketing company is trying to figure out the popularity of their soda products, and they list the preferences between males and females. Obviously, this is a big important to any company that's marketing something to somebody else. They want to know who likes it and who doesn't like it. So they typically do studies seeing if either males or females like it, or certain age groups also. There's all sorts of things that are involved in it. But nonetheless, let's go ahead and treat this here. And as far as you're concerned, a person liking one drink or another is a 50-50 shot. So you don't know whether they're going to like it more or one more or less than the other before you ask it. So these can all be considered part of the same types of problems that we've been doing. Now, let's take a look. If a person is selected at random from the survey, answer the following questions. That's what I'm going to answer. So my questions will be this. A, what is the probability the person was female? So the probability that they're female, we simply need to look at the total of all females in the group compared to the total of the group. So the event would be all female. So let's take a look at the probability of being a female. And I didn't mean to put an E, I meant to put an F for female. So if we take a look at that, we look at the total number of females is 105. So if you will, the size of the event is 105. The total number of people, the size of the sample space is right here. N of S equals 252. So that goes down there. You can leave it like that. I wouldn't even bother simplifying it. What is the probability that the selected person favors soda Y? So once again, if I look at the probability of Y, we already know that there's 252 total. For Y, all we have to do is look at the Y column. We have 68 males liked soda Y and 13 females liked soda Y for a total of 81 together. And you could leave the answer like that. What is the probability of the selected person being someone who likes soda Z and is female? So now when we look at this, we need the intersection of the column and row in this situation. So we need the intersection of female with soda Z, and that's a total of 45. So the size of this event is 45. And the probability, you could do something like Z and F, like so, is 45 over 252. Finally, what is the probability of the selected person liking soda Z or Y? So here they can like either one of those, Z or Y. So what you do here is you add up these two quantities. These are the number of people that like Y. These are the number of people that like Z. So together is the collection of people that will take either one of them. So here, let's get our N of E. That will be 81 plus 102. So let's make sure we have that. That's at the bottom of column Y and at the bottom of column Z. And that is equal to 183. So the probability of that event occurring is 183 over 252. So before I finish, let me just say one last thing that I didn't mention it, but no matter what, the probability of something is always forced to be between 0 and 1. So the probability of anything occurring is between 0 and 1. And the probability equals 0 means it can't happen. So if a probability equals 0 means there's not even theoretically possible. Then P equals 1 means it is certain to happen. Rarely is there anything in life that you have certainty like that, but a lot of people think the sun coming up in the east is as reliable as it gets. So we might say the probability of such an event is 100%, or 1, meaning that it is guaranteed to happen. Now, various things in between is where we live. So you've got the probability of 0 on the one hand all the way up to the probability of 1, which is certainty. So can't happen, certain to happen, and then as you go this way, you're going to become more likely that it happens. So that as you go in that direction, the probability gets higher. But should you go in this direction here, this is where it's less likely to happen. And we'll talk about more properties of probability after this in the next sections.